Hey guys, welcome to our first experimental virtual lecture, as it were. We're going to be picking up with buffered solutions because that's where we left off last time. Hope you guys are all able to get these videos properly, and if not, please let me know. Also, I hope you think it's as hilarious as I do that I now have a YouTube channel because it's really weird for me. But anyways, let's pick up with buffers. So we talked about buffers last time. We talked about how a buffer needs to be made of a weak acid conjugate base pair. And we talked about the reason why is because strong bases and strong acids completely dissociate. So if you were to mix them together, you would end up with a pH of 7, and that can't buffer anything. That's just a neutral salt solution. So we need mixtures of weak acid and bases. And this is what we call a buffer, right? And a buffer is going to contain both the weak acid that will neutralize small amounts of base that you add, and it will have a weak base component that will neutralize small amounts of acids. But remember, buffers are not the champions of the world. They have a limit to which they can actually do this. So we oftentimes can't use a buffer over a very large range, okay? So buffers have to be over a small range. And here are some examples of buffers that we talked about last classes. So here we have acetic acid and the acetate ion. That together would be a great buffer solution. Or we have ammonia and ammonium. So the base ammonia and its conjugate acid ammonium. And that would also be a great buffer solution. But depending upon where you want to buffer, you would want different concentrations of these relative to one another and potentially different combinations to buffer at different pHs. So let's talk about how we would actually calculate these things. Okay, so here is our generalized acid, weak acid dissociation, right? Here I've substituted A for X, but other than that, it's exactly the same as what you've seen before for the Ka expression, okay? And you know that K is always concentration of products over reactants, so it's the concentration of the proton times the conjugate base divided by the concentration of the acid. Now, if we rearrange this, though, for the concentration of the proton, we see that, so basically how you do that, right, is you multiply both sides by the concentration of the acid, and then that gets proton almost by itself, but then you have to divide by the concentration of the X minus, and then you end up with the expression that we see below. And this shows us what the proton is dependent upon. So if you look here, the concentration of the proton is dependent upon two primary things. One of them is the Ka, which is going to change depending upon what the weak acid component of the buffer is, right? So the higher the Ka, the more acidic a substance is. The lower the Ka, the less acidic a substance is. And then the other thing that it depends upon is that fraction, right? The fractional amount between the concentrations of the acid and the base. So this is what's going to determine the concentration of the proton, which will then determine the concentration of, or not the concentration, but will then determine what the pH is, right? Because pH is the negative log of the concentration of the proton. So here's an example of how a buffer would actually function. So here in the center of the screen, we have hydrofluoric acid and the fluoride ion, and we're going to then add a little bit of base to this, okay? And when we add a little bit of base, what needs to react with that base is the acid. So you see that the concentration of the acid is going down a little bit as some of it is consumed to react against the base. And then the concentration of the conjugate base actually goes up. But notice these concentrations are not changing dramatically, meaning this buffer would not work at really high concentrations. If you look at the other side, you see the exact opposite, right? If we were to add protons to this buffer, the fluoride ion, which is the base, would react with the protons. Thus, the concentration of the fluoride ion would go down and the concentration of the acid would go up. Again, not very large differences here, but that's because the concentration is not dramatically changing because we haven't added a large amount of protons. This is a small amount of protons that we are trying to buffer. So, since buffers are made of conjugate acid-base pairs, this is essentially just a common ion problem, right? So you can use the exact same procedures that we started this chapter off and our last lecture in class covered. How basically we just have an ice table, but we have an ice table where we start with reactant and some product. But I'm sure you guys are probably getting a little tired of ice tables, and honestly, I am too. Nobody likes solving an ice table for the 50 billionth time. So I'm actually going to show you an equation that can be used instead of an ice table to answer these types of questions. And then I'll prove it to you as to how it works. Okay? So how we're going to do this is we're going to start with our equation that solved for the concentration of the proton. So the concentration of the proton is equal to Ka times acid concentration divided by base concentration. Now, what we can then do is we can take the negative log of both sides of that reaction, because you know, according to the rules of algebra, what you do to one side, you must also do to the other side. So we're going to take the negative log of both sides. Now, you guys immediately know what the negative log of protons is, right? The negative log of protons is pH, right? And then the other negative log, we can actually just distribute that to the two portions of that parenthesis. So it's the negative log of Ka minus the log of concentration of acid over base. So negative log of protons, that's pH. Negative log of Ka, that's pKa, right? So now we're seeing things that we're familiar with. We're seeing things that we've already discussed in this class. So we can rearrange this equation to then say that pH is equal to pKa minus the log of the concentration of acid over the concentration of base. However, don't ask me why, but people decided that this is not the form that we are going to have people memorize because we don't want to have a minus log in our equation. We want it to be a positive log. Well, I know that at this point, some of you may or may not have had the math that explains how logarithms work. I'm really not going to go into it because it doesn't really matter. It's just, trust me when I say that if you turn that from a negative log to a positive log, it flips the fraction. Okay? So instead of the concentration of the acid over the base, now it's the other way around. It's the concentration of the base over the acid. And this final equation is what you're going to memorize, and that is known as the Henderson-Hasselbalch equation, named after the two scientists who are associated with developing it. So it is simplified as saying the pH is equal to the pKa plus the log of the concentration of base over the concentration of acid. Okay? And we can calculate the pH of a buffer. Basically, if you want to know the pH of a buffer, all you have to know is what's the acid component, because you get the Ka from that, and then you need to know initial concentrations. This means you don't have to sit here and solve an ice table to get the equilibrium concentrations. You can use initial concentrations. And that's the big win of the Henderson-Hasselbalch equation. I don't have to do all the work to get the equilibrium concentrations. But I don't necessarily just want you to take my word for it, though. I want you to actually see how it can be used. So what we're going to do in the next couple minutes, or in the next short video, is we are going to practice this both ways. We're going to practice it with an ice table, and then we're going to practice it using the Henderson-Hasselbalch and see that really there is no change, there is no difference. It works just fine, right? And why we can get away with this equation, as it says on the slide, you can normally neglect. Remember how we ignored that minus x and that plus x before when we talked about ice tables associated with common ions? If we're going to ignore that anyways, then we are saying that the initial is the equilibrium, right? If I say the minus X doesn't matter, then initial is equilibrium for the acid. And if I say the plus X doesn't matter on the conjugate ion, then I'm saying that the initial concentration of the product is the same as the equilibrium. So if they're gonna be the same anyways, why not just avoid the ice table altogether? Okay? All right. So this is the end of this video. There are more videos to come. The school heavily recommended that we try to keep our videos short to make them easier to buffer and load for you guys. Okay? So what that means is we are not done with the lecture, right? You need to now go to the next video. All right? So I will see y'all in just a couple seconds.